Okay, so last lecture हम लोगों ने formal charge किया था, right? And we also said कि depending upon the calculation of the formal charge, we can say or we can manipulate the most stable structure, right? So today we are going to go on to the next topic, which is polarity of covalent bonds. Let's understand what this polarity of a covalent bond is. We are taking into consideration two types of molecules. The first one, which are known as homoatomic molecules. Homoatomic molecules कौन से होते हैं? Those molecules which have same kind of atoms. Right? So homoatomic molecules are those which have same kind of atoms. Now, the other type of molecules which we are going to discuss over here, they are known as what? Heteroatomic molecules. Heteroatomic molecules are those which have different kind of atoms. ठीक है? So examples of homoatomic we can take is oxygen, we can take fluorine, chlorine, nitrogen. All these they are said to be homoatomic. Heteroatomic we can take carbon dioxide, HCl, HF, SO2, water. All these they are heteroatomic molecules. Now in case of homoatomic molecules, in fact in both the cases the bonding is done due to sharing. Okay, because we are saying that in both these cases the kind of bonds which are present, they are the covalent bonds. So sharing of electrons is going to take place in order to form a bond, right? So if we are taking an example of say fluorine. In case of fluorine, we know it has 7 electrons. So there is one shared pair of electron which is present. 7 electrons we can draw like this according to the Lewis dot structure. ठीक है? उसी तरह से यहाँ पे also there are 7 electrons which are present. Right? So when we combining these two atoms to form the molecule, we say that each of the fluorine shares, as a result of which the molecule of fluorine can be represented in this manner. Right? Now, when we are looking at homoatomic atoms, we say homoatomic molecules, we say that the shared pair of electrons that remains in the center. Why it is remaining in the center? Because fluorine and fluorine both are the same atoms. They have the same electronegativities, as a result of which they are equally going to attract the shared pair of electrons towards itself, as a result of which the shared pair remains in the center. Such molecules in which the atoms do not have any electronegativity difference and the shared pair of electrons remain in the center, in case of diatomic molecules, they are said to be non-polar in nature. So this criteria of not having polarity or the shared pair of electrons which is remaining in the center, this criteria can be explained for diatomic molecules. Okay. Now in case of heteroatomic molecules, there are different kind of atoms. Let's take the example of HF over here. When we are taking the example of HF, we know that fluorine is more electronegative than hydrogen. As a result of which, what fluorine will do? It will attract the shared pair of electrons more towards itself. So we can show the attraction by the arrow over here. It attracts the shared pair of electrons more towards itself, as a result of which it gets a slight negative charge and hydrogen gets a slight positive charge. So in this molecule there are two different poles which are developed. Because of the development of two different poles, such molecules, they are said to be polar in nature. Polar in nature or polarity, it exists due to difference in electronegativities of the two two bonded atoms, right? So there is a electronegativity difference, because of which in HF the fluorine that is going to attract the shared pair of electrons towards itself. Basically, what do we say when we are talking of polar bonds? We can compare it with a game of tug of war. You know what happens in tug of war? There is a rope, okay? There are two teams present. So both the teams, they are trying to pull the rope towards themselves. The stronger team can pull the rope more towards itself and that team wins, right? So same thing is happening over here. Here also the stronger team, which is the more electronegative atom, that pulls the shared pair of electrons towards itself, getting an achievement on the basis of the fact that it gets a negative charge on it, right? So such molecules which have different poles created due to difference in electronegativity, they are said to be polar. Okay? So in this, we can say that if you want to now define what a polar covalent bond is, you can write down. What is a polar covalent bond? A covalent bond in which the electrons are, a covalent bond in which the electrons are shared unequally, electrons are shared unequally, and the bonded atoms acquire a partial positive and negative charge, a partial positive and negative charge is called polar covalent bond, is called polar covalent bond between two dissimilar atoms, between two dissimilar atoms, between two dissimilar atoms. So this is what a polar covalent bond is. Now when we are representing a polar covalent bond, we can represent a polar covalent bond by giving a slight positive charge on this and a slight negative charge on this. Okay? Or we can also represent a polar covalent bond by giving an arrow like this, in which the shared pair of electron is attracted towards the fluorine. Now these kind of bonds, they are intermediate. They are intermediate between the ionic and covalent bonds, which means that they are not as strong as ionic bonds, but they are stronger than covalent bonds. So there is not completely electrostatic forces of attraction which are present in these bonds as in the case of ionic bonds, but still they have slight partial charges, so as a result of which they can be said that they have partial ionic character. Okay? Now bond polarity is described in terms of ionic character. As you can see over here, there are two different ions which are developed, and with increase in electronegativity, the polarity that is going to increase. Increase in difference in electronegativity, the polarity increases. Okay? Increase in electronegativity, the polarity that is going to increase. So let's take example of few of the compounds over here. Right? Just for example, if you're talking of the molecule HF, the electronegativity of hydrogen, that is 2.1, whereas the electronegativity of fluorine, that is 4.0. So when we are looking at the electronegativity difference over here, the electronegativity difference that comes to 1.9. Okay. Similarly, if we are going to HCl, again the electronegativity of hydrogen, that is going to be 2.1, whereas the electronegativity of chlorine, that is 3.0. So the electronegativity difference over here, that comes to 0.9. Okay. Then when we look at HCl, again the electronegativity of hydrogen is 2.1 and that of bromine is 2.8. So the difference over here, it is 0.7. Okay? And when we are looking at hydrogen iodide, over here the electronegativity of hydrogen is 2.1, whereas the electronegativity of iodine, that is 2.5. So the difference over here, that comes to 0.4. Depending upon the electronegativity difference, the maximum electronegativity difference, that is in case of HF, right? So HF is going to be most polar, then HCl, then HBr, and the least polar, that is going to be HI. So polarity, it depends a lot on what? It is going to depend upon the electronegativity difference. Now when we are looking at the ionic character, greater the electronegativity difference, more is going to be the ionic character. So amongst all of this, HF, that is going to be most ionic. Then we come to HCl, then we come to HBr, and then we come to HI. Okay? So this is the trend of ionic character of halogen acids. Now according to Pauling, the percentage of ionic character, that can also be calculated on the basis of electronegativity difference. Okay? जैसे let's just draw a table. We are saying that XA, XB gives the electronegativity difference. Then percentage of ionic character, and nature of AB bond. All these, they are interlinked. Okay, let's just see a few examples to make this more clear. In case the electronegativity difference, that is 0, like we did just now in homoatomic molecules, if the electronegativity difference is 0, then the percentage of ionic character is also going to be 0. Okay? And the molecule, that is going to be purely covalent. Okay? उसके बाद if the electronegativity difference is between 0.1 to 0.8, the ionic character over here is anything between 0.5 to 15%. Okay? And such molecules, they are said to be covalent. They also do not have any ionic character. So we are saying they might not be purely covalent, but still they are predominantly covalent. Now if the electronegativity difference is between 0.9 to 1.8, okay? In this case, the percentage is 19 to 47% of ionic character. So these kind of bonds, they are said to be polar covalent. This is an important table over here because generally the questions, they give you the electronegativity difference, and on the basis of that you have to manipulate the nature of the bond. ठीक है? फिर उसके बाद if the electronegativity difference, it is 1.9, right? So in that case the percentage of ionic character is 50%. Okay? And we say that the bond is 50% ionic and 50% covalent. ठीक है? It is 50% ionic and 50% covalent. And if the electronegativity difference is anything between 2 to 3.2, then the ionic character, that can range from 55% to 93%. In this case, the bond that is going to be predominantly ionic. Okay? Have you understood? So on the basis of electronegativity difference, we can calculate the percentage of ionic character. So just see once again, the question which comes from here is that they tell you that the electronegativity difference that is equal to 1.9, which is the nature of the bond. So you have to remember that if the electronegativity difference is less than 1.9, then the bond is predominantly covalent. And if it is greater than 1.9, then it is predominantly ionic. And if it is 1.9, then it is 50% covalent and 50% ionic. Okay? So this one figure which you have to remember over here, that is 1.9. In certain books, 1.7 is also given. So you can also talk of 1.7 over here. Okay? Clear ho gaya? Then next we go on to the calculation of percentage of ionic character. Percentage of ionic character. There was a scientist by the name of Henry and Smith. They gave us a mathematical expression to calculate the percentage of ionic character. According to this, percentage of ionic character that can be given by this relation, that is 16 XA to XB plus 3.5 XB का square, where XA, XB represents the difference in electronegativities of atoms A and B. Okay? So this is how we can calculate approximately the percentage of ionic character. So we have already said that if the percentage over here that comes equal to 50, by calculating the percentage by this expression, the answer which you get is 50, then in that case the bond that is going to be 50% ionic and 50% covalent. ठीक है? समझ आ गया? Okay. Now when we are doing this, the polarity, we come to another property which is known as the dipole moment. Dipole moment is the measure of polarity, and the value of dipole moment tells us whether the molecule which is given to us, that is polar or it is non-polar. Okay? So this is basically, it is a, you can say that dipole moment is a numerical scale to measure polarity. Right? Greater the value of dipole moment, greater is going to be the polarity, and more is going to be the percentage of ionic character. So this you need to remember over here. Now how do we calculate the dipole moment? Mathematically, dipole moment that is given as Q into D, where Q is equal to charge on the molecule. Okay? And D that is going to be equal to the bond length. Right? Now generally what we do is that we calculate the dipole moment, the unit for dipole moment, that is Debi, or it is represented by capital D. The value of 1 Debi, that is equal to 10 raised to power minus 18 electrostatic unit, ESU. Okay? And because we are also taking the bond length over here, so centimeter. Right? Where electrostatic unit is the unit for charge and centimeter is the unit for length. Okay? In case of coulomb meter, this is given as 3.33 into 10 raised to power minus 30 coulomb meter. Okay? Now value of dipole moment, the value of dipole moment increases with increase in electronegativity. ठीक है, increases with increase in electronegativity. So we can say that if the value of mu is large, right, then in that case the compound that is going to be polar in nature, and if the value of mu that becomes equal to 0, such molecules are non-polar in nature. ठीक है? Now while calculating the value of D or manipulating the value of D, we have to keep one thing in mind. We say that the dipole moment is a vector quantity. ठीक है? Now if it is a vector quantity, it will have both magnitude as well as direction, right? So depending upon this, if the overall dipole moment is greater than 0, then those molecules, they are said to be polar, and if the overall dipole moment that is equal to 0, those molecules, they are said to be non-polar. Why are we talking about the net dipole moment or overall dipole moment? Now over here we are going to discuss polyatomic molecules. Polyatomic molecules are molecules which have more than 2 atoms. Okay? Now in this case we say that one more thing which you can write down over here is that a symmetrical molecule has the value of mu as 0. Therefore, this is going to be, all these molecules, they are going to be non-polar in nature. ठीक है? जैसे for example, if you are taking the example of carbon dioxide, in this case we know that oxygen is more electronegative, so the dipole is directed towards oxygen. In a similar manner, over here also, the dipole will be directed towards oxygen. As a result of this, the resultant dipole moment of this molecule, that becomes equal to 0, and therefore carbon dioxide, that is non-polar in nature. ठीक है? Similarly, we have a molecule, say we are taking BF3. So over here fluorine is more electronegative, over here also fluorine is more electronegative, and over here also fluorine is more electronegative, right? Now in all the cases, as fluorine is more electronegative, when we are looking at the net dipole moment over here, that also becomes equal to 0. ठीक है? So for these molecules, as mu that is equal to 0, both the molecules, they are going to be non-polar in nature. Whereas when we are talking of unsymmetrical, molecules, they all have a resultant dipole moment. They have a set value of mu which is going to be greater than 0. Then such molecules, they are said to be polar in nature. ठीक है? समझ आ गया? Let's take a few examples over here also. Okay, so when we talking of, say, water, this is the molecule of water. In this case, we know that oxygen, that is more electronegative, right? So in here the resultant dipole moment that is going to be added. So we say that mu over here, that has a value of 1.84 dB, right? It is an unsymmetrical molecule with with a value of mu as 1.84 dB. Therefore, this is going to have a net dipole moment of this. So the molecule that is equal to polar. Okay. Similarly, let's take the example of sulfur dioxide. This is the molecule of sulfur dioxide. Over here, oxygen is more electronegative. Okay. So in the same direction again. So the value of mu for this molecule that is equal to 1.60 dB. So this is also a polar molecule. Then we can take the example of NH3 over here. This is NH3. Over here nitrogen is more electronegative, and this also the vector that goes towards the lone pair of electrons. Therefore, here also there is going to be a net dipole moment which is equal to 1.46. Okay. Now the question over here comes, does the net dipole moment of unsymmetrical molecules only depend upon the electronegativity difference? No. Or the even for that matter symmetrical molecules, it will over here when we are seeing all these examples. In carbon dioxide there is a great electronegativity difference between carbon and oxygen. Still we are saying that the dipole moment of this molecule that is 0. So basically the net dipole moment will not only depend upon the electronegativity difference, but it will also depend upon the structure or geometry of the molecule. Okay. A very good example which we can take over here is that of NH3 and NF3. This is the molecule of NH3 and this is the molecule of NF3. Okay. Now in both these cases we can see that fluorine that is more electronegative than hydrogen, right? But still we say that the dipole moment of NH3 is greater than that of NF3. Now why this is happening? This can be owed to the structures of both. In case of ammonia, nitrogen that is going to be more electronegative. ठीक है? Lone pair of electrons की तरफ जाएगा. So resultant dipole is all in the same directions. Therefore, the resultant dipole over here that is going to be greater. But when we are talking of NF3, so this is fluorine being more electronegative. The electrons will be attracted by all the fluorine. So the net dipole moment of this will be a subtraction module, as a result of which this is going to have less dipole moment. So NH3 is more polar than NF3 in spite of the fact that fluorine is more electronegative than hydrogen. Okay? Now how do we calculate the net dipole moment? In order to calculate the net dipole moment, let's say that we have a molecule A which is bonded to B and C. Okay? Over here, let's say that the dipole moment of this that is going to be equal to mu1. The dipole moment of this is equal to mu2, and the resultant dipole moment we can draw like this. So this is the resultant dipole moment. Okay? Now over here, both the two polar bonds, they are inclined at an angle of theta. Right? Now in order to calculate, we say that there is a partial positive charge on A over here, there is a partial negative charge on B, and a partial negative charge on C. So resulting dipole moment that is given by the expression under root of mu1 square right, under root of mu1 square plus mu2 square plus 2 mu1 mu2 cos theta. So this is how you can calculate the resultant dipole moment if the dipole moment of mu1 and mu2 is given to you and theta is also given to you. So you will have mu resultant that is equal to mu1 square plus mu2 square plus 2 mu1 mu2 into cos theta. Okay. Now in this case we say that if the value that of theta that is equal to 0. Okay. If the value of theta is 0, then we say that the value of mu r that is maximum. Okay, so this generally happens for diatomic molecules. Theta that is going to be equal to 0 for diatomic molecules. Therefore, the resultant dipole moment that is going to be maximum. But if in case we say that we are taking the value of theta as 180 degrees centigrade, in that case mu r will have a minimum value. Okay? As in the case of carbon dioxide which we did, in which over here you can see that the bond angle over here that is equal to 180. So if it is theta is going to be 180 over here, in that case the resultant dipole moment that becomes equal to 0. Okay? So let's go on to the applications of dipole moment. What are the applications of dipole moment? Some of them we have already discussed. The first application is to decide the polarity of the molecule. To decide the polarity of the molecule. So we have already discussed that if the value of mu is going to be greater, the molecule that is going to be more polar, and if the value of resultant dipole moment that is less, then the molecule that is going to be less polar. Okay? Then number 2, it also helps us to calculate percentage of ionic character. Percentage of ionic character in a molecule. So percentage of ionic character के लिए we have to know two values. One which is known as the theoretical value of dipole moment, which is calculated as Q into D, and the other one that is the experimental value, which is determined experimentally. Now in order to calculate the percentage of ionic character, it is given by experimental value, upon theoretical value into 100. ठीक है? Experimental value upon theoretical value into 100, that is going to give us the percentage of ionic character. Now in this questions, experimental value will be given to you in the question, but you need to calculate the theoretical value. Okay, let's just do an example over here. We are doing the example of hydrogen chloride in order to calculate the percentage. Now over here they have given us the value of Q as 4.8 into 10 raised to power minus 10 ESU. Okay? And the value of D they have given to us as 1.27 Armstrong. Right? So this has to be converted into centimeter. It will be equal to 1.27 into 10 raised to power minus 8 centimeters. Okay? What is going to be the value of mu? So we say that mu theoretical, that is going to be equal to Q into D. The value of Q is given as 4.8 into 10 raised to power minus 10 into 2.7 into 10 raised to power minus 8. So when we calculate this, it comes to 6.09 dB. It is coming to 6.09 dB. The mu experimental, that is observed to be 1.03. So in order to calculate the percentage of ionic character, the formula we use is experimental value upon theoretical value into 100. So experimental value कितना है? 1.03 upon 6.09 into 100. ठीक है? So the ionic character which is coming over here after calculating this, that is 16.9% ionic. So this is how you can calculate the ionic character. This is the second application. The third application is to determine the geometry of molecules. To determine the geometry of molecules. We have already studied that all the symmetrical molecules, they have a zero dipole moment. ठीक है? And they are said to be non-polar in nature, while the unsymmetrical, they have certain set values of dipole moment and they all are said to be polar. So molecules like carbon dioxide and CS2, they have a linear geometry. Right? So as a result of this, the value of mu for such molecules, that is going to be equal to 0, and such molecules, they are non-polar. ठीक है? Now water also can have a linear geometry, but it is already stated that mu has certain set, water has certain set value of mu 1.84 dB. ठीक है? So because of that, we said that water does not have linear geometry it has a net dipole moment. So the geometry of water, that is bent or angular. ठीक है? Similarly, we say that in case of ammonia, the three nitrogen bonds are not symmetrically arranged. Three hydrogen bonds are not symmetrically arranged. So because they are not symmetrically arranged, they have a net value of dipole moment, ठीक है? And therefore they do not have a structure similar to BF3. NH3 and BF3, both of them are tetraatomic molecules. In case of BF3, we are saying that the dipole moment is 0 because all the fluorine atoms, they are symmetrically arranged around boron. Whereas in NH3, the arrangement is not symmetrical, therefore it has a net dipole moment, giving it a polar character. ठीक है? Then the fourth application is to distinguish between cis and trans forms. To distinguish between, fourth is cis and trans forms. Now let's first understand what is this cis and trans terms which we are using over here. Cis and trans means that they are geometrical isomers. Geometrical isomers means that whenever two carbon atoms, they are attached with the help of a double bond, then the rotation of the carbon atoms, that is restricted. We cannot freely rotate the carbon atom to 360 degrees. That is known as steric hindrance. ठीक है? Or it is known as restricted rotation. This we will do in organic chemistry in a greater detail. For now, just for you to know what cis and trans means, I am explaining this. For example, if we are taking a molecule like this, ठीक है, in which there is carbon-carbon double bond present. So what are we saying? That if we are keeping this stable and we are trying to rotate this, We cannot rotate it to 360 degrees, we can only rotate it to 180 degrees. So when we rotate it to 180 degrees, then what is going to happen? The molecules or the atoms or group of atoms which is attached to the first carbon atom do not change their places, whereas this is going to change the place. Okay. Now in this you can see that the same kind of atoms, they are on the similar side. So this is known as a cis isomer. Okay. Whereas over here they are on the opposite sides. So they are known as trans isomer. The value of dipole moment helps us to distinguish between cis and trans. We say that for trans isomer, the value is going to be, value of mu, that is going to be 0. Okay? And for cis isomer, the value is greater than 0. Okay? So this can be easily said by taking that cis has higher melting points than trans, because they have certain percentage of ionic character. Is it clear? But sometimes what happens is that if there are two different groups attached, then this case does not happen always. That trans will always have a zero dipole moment lesser than cis. It depends upon the atoms which are arranged or which are attached to the carbon. Okay? Just for example, if we are talking of a molecule, say we are taking this molecule. Now what is going to happen when we will rotate it? Hydrogen is going to take this place. Okay. So if hydrogen is taking this place over here, the similar groups are on the same side. So this is going to be cis, and this is going to be trans. Okay. Now in this case, because we say that chlorine is more electronegative than carbon, the dipole is directed towards chlorine. In this case, we say that the methyl group which is present over here, that is an electron donating group. So if it is donating electrons, it will donate towards carbon. Now when we are looking at the resultant dipole moment over here, we see that the dipole moment of trans, that becomes greater than the dipole moment of cis, in which in cis you can see that both the dipoles, they are in opposite directions. Both are in the opposite directions. So the value of dipole moment for cis, that is going to be greater. Okay? Is it clear? Then the last application is to determine the orientation of the benzene ring. Both these are very important with respect to organic chemistry. To determine orientation of benzene ring, right? When we are talking of orientation of benzene ring, we say that if we are calculating the mu for, let's say, we are taking orthodichlorobenzene, okay? We are taking metadichlorobenzene, and we are taking paradichlorobenzene. Okay? In this case, the value of mu for ortho, that is going to be maximum. It is 2.54 dB. Okay? For meta, it is 1.48 dB, and for para, mu is going to be equal to 0. Okay? Why this is happening? Because chlorine is more electronegative, so the dipoles, they are directed towards opposite sides. Okay? So this you need to remember, that the dipole of ortho, that is going to be maximum, then para, and then meta. We will come back to these two points when we do organic chemistry. ठीक है? Then the last topic which we are going to do, that is partial covalent character in ionic bonds. Partial covalent character in ionic bonds. Now, as we just studied that all the covalent bonds, they have partial ionic character depending upon the value of dipole moment. In a similar manner, every ionic bond also has certain amount of covalent character in it. ठीक है? Now this covalent character, that is explained on the basis of a term which is known as polarizability. ठीक है? What do we understand by polarizability? Now we say that when two oppositely charged ions, that is, we have a cation and an anion, ठीक है? Whenever they are brought together, the positive charge that is going to attract the outermost shell of the anion. Okay, because positive charge that is deficient of electrons. So what it is going to do is that it is going to attract the outermost shell of the negative charge of the anion towards itself. As a result of which it distorts the electron cloud of the negatively charged anion. And this is known as polarizability. Okay? So if we, for example, if we have, let's just try to depict it with the help of a figure. Let's say this is A, this is a purely ionic bond. Okay? Now in this case, the positive charge that attracts the electron cloud of the negative charge, as a result of which the electron cloud of the negative charge that becomes distorted. So you can see over here that the electron cloud that is becoming distorted. This is known as polarizability. ठीक है? So we say more the polarizability, more is the covalent character. More the polarizability, more that is going to be the covalent character. So this set of polarizability or covalent character that is explained on the basis of Fajan rules. This is very, very important. We generally get one question from this section. So please understand this very carefully, okay? Now, according to Fajan rules, number 1, it is said that smaller the size of the cation, smaller the cation, more is the polarizability, and hence more is the covalent character. Now why this is happening? Because if the size of the cation is small, then in that case the nucleus or the nuclear charge will more effectively reach to the outermost shell. Okay, so as a result of which it will more distort the cloud of the ion, the anion. That is why we say that smaller the cation, more is the polarizability, and hence more is going to be the covalent character. So if we are taking the salt of alkali metals, we are taking lithium chloride, we are taking sodium chloride, then potassium chloride, rubidium chloride, and cesium chloride. So if you get a question like this, in this which is going to be the most ionic or the most covalent. So smaller is the size, more the polarizability, more is the covalent character. So covalent character decreases down the group. ठीक है? So in this case, lithium chloride, it is most covalent, and cesium chloride is most ionic. ठीक है? Clear हो गया? Then second, larger the size of anion, more is the polarizability. Okay, so if the size of the anion that is going to be more, it will be more effectively distorted by the cation because it is in greater reach to the nucleus of the cation. Okay, so over here again, if we are taking salts of lithium, we are taking lithium fluoride, lithium chloride, lithium bromide, and lithium iodide. In this case, we are saying larger the size, more is the polarizability, so the covalent character will keep on increasing. Okay? So this is going to be most covalent and this is going to be least covalent. Okay? Is it clear? Okay. Third, it depends upon the charge. So we say greater the charge, whether on the cation or on the anion, either of the two. More the charge, more is the polarizability. Okay, more the charge, more is going to be the polarizability. So if we're talking of NaCl and we're talking of calcium chloride, then calcium chloride is going to be more covalent with respect to NaCl. Because the charge of Na, it is 1 positive and the charge of calcium, it is 2 positive. Okay? Then last, even electronic configuration has an effect on polarizability. So when we are talking of electronic configurations, it is said that all systems having 18 electrons, right? 18 electron systems which are known as pseudo-noble gas configuration. 18 electron means that they are either losing or they are gaining. To make 18 electrons in the outermost shell, they are going to be more covalent than the 8 electron systems which are less covalent. Let's explain this by taking an example of sodium. We know that the electronic configuration of sodium, that is neon 3s1. Okay. So for Na positive, the electronic configuration is that of neon. The electronic configuration of neon is 1s2, 2s2, 2p6. Okay. So in this, the outermost shell has 8 electrons. Whereas when we are talking of copper, the electronic configuration of copper, that is argon 4s1 3d10. Okay. And if we are taking Cu positive, then the electronic configuration that becomes equal to that of argon 3d10. Okay. So 3d10 means it will have 3d10 and then it will also have 3p6 and 3s2. Okay, na? So outermost shell will have 10 of D, 6 of P and 2 of S. So total becomes equal to 18. So this is going to be more covalent with respect to Na. So if we are taking a salt CuCl, that is more covalent with respect to NaCl. Right? So this topic is very, very important from your competition point of view. Okay? So today we are going to do only till here.